Now that Firefly's Blue Ghost Mission 1 is completed, I have two things we need to look into. What will happen with their mission number 2? And then second, how can we use this mission as a great idea for a lesson plan for an astronomy unit? So let's see if we can put together all the thoughts. We're going to start first looking at the different experiments that happened for mission 1. We're going to see that Firefly is already asking for submission for new experiment to send with mission 2, which is planned for 2026. And then I'm going to make parallel on how we can make this project, the Firefly's Blue Ghost mission 1, as a great way for lesson plan and experiment in your astronomy class. And let's see if we can even think of what are new experiments that students could think of for mission 2. So this is the plan for this mission and this video, and hopefully you will appreciate. And all along the video, if you have any comments, clarification, questions, or even suggestions, don't hesitate to put them in the comments below. First of all, we have Firefly that shared with us on March 17 that their mission number 1, was complete, and all the experiments worked out nicely, and they went even beyond. So we're going to talk about the different experiments as we go along. And the reason why I want to spend time with you with the experiments is to show you that many of those are very simple ones to bring humans a lot of new data and great science. And that's important because if you go with on the Firefly's website, they have an upcoming mission, Blue Ghost Mission 2, and they are already having a few things with a lunar pathfinder. They also have the lunar surface electromagnetic experiment at night, because guess what? I think they want to go on the far side of the moon. We have the user's terminal UT and seismic payload interplanetary discovery, exploration, and research. And if you go here a little bit, it says here our ride, and the reason for that, if you look, it says here that they want a full spacecraft track. There you go. And that means that if I look a little bit beyond, it says here, look at this. Why don't we join their mission? So it says here, Blue Ghost Mission 2 still has payload capacity available for additional customers with deployment options and services available in lunar orbit and on the far side of the moon. So there we go. It's confirmed they're going on the far side. So get in touch with them to see what you can contribute. And at the same time, it's raising funds for them. So let's see if we can have a good idea about what happened for mission 1 and how we can take these experiments for our astronomy classroom. So let's see. So first of all, let's go back to here and let's have a quick look. How's the writing here? So here we have, so when I started the video I shared here, this is the sunset. This is the end of the journey of Firefly's Blue Ghost mission 1. The sun here was going away. If I remember well from what I read, it was the end of the energy from the batteries of Firefly. And some of you will say, okay, how come they have a sunset right now? So let's see if I can share with you where they were. So if we take this, this video here is from NASA when they launched the mission. So here they are right here in this place right there. And what happens is that they chose this area because it was very flat, gives them a chance to see. So it's like a flood plain or a magma plain. And what happens, so here you could see it's a very flat surface, a great place to be able to do some of the equipment they wanted to do. And at the same time, if you look, this is a picture of a new moon, all dark, but you can see here the place where they landed. So if I show you the different phases of the moon, so here we have the new moon and we have the waxing crescent. So they landed where they could be right here. I'll show you the picture. I don't know if I can make it bigger. There you go. It's this place right here. So what happened with the first crescent, they were able to get some energy, and at that time they could start their experimentation. They were able to go from the first quarter and then the waxing gibbous. Then they had the full moon, and at that time they were able to do also a solar eclipse from the moon when the Earth passed between the moon and the sun. That was exciting. However, as soon as the full moon occurred, then we have the waning gibbous. And what happened here, we end up with the beginning of the light going on one side of the moon, and here we have the dark side. So here, not having any light, the battery and the solar panels could not work on Firefly's Blue Ghost mission 1. So here, that was the end of this, and that's why we have a mission that more or less ended on March 17. Because if I remember well, the first crescent right here was on March 1st, and because they have a cycle of about 29 days, the full moon being on March 14th, 15th, that brings us here to the end of how it worked. So that's basically how it worked right here. Perfect. So let's see what were the experiments. It's always nice to see what they are, and I'll make analogies with what people can do, what teachers could do in their classroom. Can we make this a little bit bigger? There we go. So let's see. So from what I could, from the information they have here, so throughout the mission, Blue Ghost transmitted 119 gigabyte of data, and that included 51 gigabyte of science and technology data, significantly surpassing the mission requirements. So let's see what are some of their work. So here is what is from the Firefly's website. And if you go, I find that NASA's website have some links that are great. So we're going to go from the Firefly's website to the NASA website. So here they communicated on March 18th the conclusion of that mission. With here this beautiful picture of a sunset here on the moon. So if we look at, let me see, so they had 10 payload on that lander. So let's see what were some of the experiment. So here we have lunar experimentation of subsurface thermal exploration rapidity. So here we wanted to know the deepest robotic planetary subsurface thermal drilling up to 3 feet, providing first of its kind demonstration of thermal measurements. Now, what would be interesting here for, I don't know if I press here, let's see what we've got. So that was the machine for this, where they were able to dig a little bit. What could be interesting for a classroom would be, let's see if I can make this image bigger. What would be interesting for a classroom would be, for example, to take a shovel or an auger and maybe dig a hole of maybe, I don't know, a foot if you can, 2 feet if you can, or let's say 25 centimeters, 30 centimeters, 70 centimeters, and try to see and measure the temperature as you go deeper on the ground. I think that could be a fun experiment, especially for thermal capacity of the ground and to see how temperature changes with depth. That's something we could do on the moon, but that is certainly something we can do on Earth as well. And keep in mind that as we go with these experimentation, the whole idea here is that if we were to go and explore a planet similar to Earth, if in our lifetime we have the resources and the capacity to travel to such planet, what kind of measurements would we want to do? And I think it's exciting that way. The other one here is the Lunar GNSS receiver experiment. And here that was to track global navigation system. And that was basically, could they use the satellite network for GPS on Earth and use those satellites to be able to send information for localization on the moon? And the whole thing here is that because we want to do more research on the moon, because Artemis project will send humans and have a stationed scientist on the moon, we want to be able to communicate with them. Now, we don't want to have a whole network of satellites around the moon because it would cost a lot of money. However, imagine if we can use our Earth system for GPS and also communication base, and then we can use that to communicate to the moon. That would be amazing. And I know that one of the things they did was to see how much delay there was between communication, so to see if it could be implemented. So that is quite amazing. So here, as you can see, they were trying to see using the lander here and being able to use the telecommunication satellite from Earth. Now, you'd say, how can we use such an experiment here on Earth? Well, something somebody could do. Somebody could probably take, let's say, an aerial photo of the school campus, and then using GPS, find the coordinates of different things on the school property. So so they could use, for example, where the soccer field or the football field is, could be about some of the sheds that could be there, specific buildings on the campus, where are the entryways, even where are the trees on the property. So that's something that could be interesting. And if teachers wanted to expand a little bit, keeping in mind that most people have a GPS and coordinate information system on their phone, they could certainly, well, you don't necessarily want to put the students home on a school project, but maybe you could ask students to localize their favorite store in your town or your city and put it on the map. And I think it could be something interesting because it's all about being able to localize specific information and location on a map. Very nice. So the next one here we have, so let's go back to this one here. So this test here was a solution for radiation. So this one is an amazing little project. So this idea here is that if you have a computer on board of a satellite or on board of at school, for example, how how are radiation and particles from the solar wind affecting here computers. Now, I was listening to a video about this one here, and it's interesting because they have the main computer and they have a parallel set of circuits and microprocessor. So what happens is that as there are particles and ionization affecting the circuits, there's a parallel checkup to see how it is affecting the circuits and the computing capacities. So I thought it was quite exciting to see how it goes. Now, you would say, how could we do something similar here on Earth? Something I could think of is if you think of a Chromebook or a computer, many students or teachers would have their own computers or sometimes an old computer working somewhere, or even an old one they could just plug. Imagine if you could take an old Chromebook and then you could see the speed of being able to do interactional calculations. And then you could see how faster or slower it works if you change the temperature. So I know that I have a friend who's fixing computers and saying that when you have a hard drive that is not working very well, it's hard to get information or it's about to break. Sometimes when it overheats, it's hard to read the hard drive. So sometimes they put it in the freezer or the fridge for an hour or two. And then when they turn it on, they have a time allocated more time to extract the information. So think if you could look at how efficient is a computer with respect to a change in temperature. So either you could have a hair dryer and adding heat to an old Chromebook, for example, to see how it would change its speed of doing calculations or working. Or if you had, for example, I don't know, ice packs or something where you can have an air conditioner blowing cold air on the computer, how would it change? I know it's not the same as radiation from the sun, but it is an experiment that someone could do in the classroom, and that will share with them why is it so important to have a fan in your computer, and sometimes you can cool with air, and with the new computers, you can do it with fluids. So that's, I think, something interesting. The next one we have here is electrodynamic dust shield. Oh, I thought this was amazing. So this one here is the idea that when you have a piece of equipment in like a, in space, what happens is that you have a lot of dust and the dust is affecting equipment and it's affecting also the suits of the astronauts. So here, this is a YouTube video. Oops. It is a YouTube video from NASA, and here they have an exciting little part right here. Let's see if I can show it to you. So they're using electrodynamic dust shield. So using electricity, magnetism, and changing in probably, I would say, charge. So what happens is that if you put dust on a piece of equipment, they can use the electrodynamics, I don't know how to say that, electrodynamically, that's a good question. They're using a shield to try to take the dust off. So let's see if it shows it here. Let's see. There was a great clip. Let's see if I can. Here's a great example. So if you have your piece of equipment here and you put dust, for example, if you have when you have a rocket landing on the moon, there's all kind of dust going up and then falling down. So if you put some dust here, when you turn on the electricity, look at this, it uses electrodynamic to move the particles away. So to actually clean or take the dust off. I think it's just amazing. And they were talking about how when the first astronaut went on the moon, one of the things they noticed was that there was a lot of dust. Oh, that's another good point here. So when they fell down, their suit was full of dust. So the idea here is that if we have, from the Artemis project, astronaut going for long-term on the moon, how can we make sure that the dust is not getting in the way of experimentation and being able to do what you want to do? So I think that's something that is quite exciting. So using electricity to dust something, I think that's something that's possible because the electricity through solar panel is available on the moon. So that is a good thing. Very nice. So let's look at the next one. Lunar magnetotelluric sounder. So here they deployed 5 sensors to study the moon's interior by measuring the electric magnetic field. The instrument allows scientists to characterize the interior of the moon almost to about 1,000 kilometers deep, about a bit more than half the distance to the moon center. So linking to the video on NASA, what happens here is that from the lander, they used they use a spring to be able to have a 40-meter by 40-meter area where, let's see, they're going to show it here. It's quite nice. So write these things right here. And what happened, it just sent ball with connective wires to be able to see how the particles from the sun are interacting with the moon, because some of them are going in the moon and some of them are changing depending on, I don't know if there's a magnetic field on the moon. That's a question I do not know, but that's something that is interesting to see. So let's see if they share with us. There you go. So they sent these, and I talked about it in my last video. So if you have this one here going 20 meters this way, 20 meters on the other way, and making it to a cross, you can have a cross section, and then you can send a voltage to see the difference in voltage with depth. And that's how they will get the information. Now, at this point, we don't have the information because all the data is exclusive to Firefly and the companies investing in them. The data will most likely be available to them only for 6 or 9 months. During that time, researchers will be able to do the analysis of the data. They'll be able to publish their papers, and then we'll be able to see what they have discovered. That will be exciting. Very nice. The next one is the Lunar Environment Heliospheric X-ray Imager. So here they use X-ray images to see the interaction of the solar wind with our planet. So here they have a video right here, and it's quite nice to see how it goes. So let's see if I can show you some good, there you go. Perfect. So here, when you have the sun and the solar wind, it is affecting the magnetism around our planet. So what happened here is that if we can, so here the sun, the sun comes from one side here. So that means that there's pressure on the one side and less pressure on the other side. We see it from Earth, from the how do you call those? Northern lights that we see from here. But then if you can study it, that's even better. So here's another example where you have the solar wind coming this way. Solar wind coming this way. affecting here some pressure on one side of the planet and low pressure of the solar wind on the other side. But there's a change in what's happening in the magnetic field. If some of these particles can go in all the way here and in between those magnetic lines to the north, or through the south here, we have the northern light or the southern light. So that's how it goes. So they have a camera. They showed it to us a moment ago, like this, that they direct towards our sun, our Earth, to be able to see the interaction. Look at this. You had to think about it. Now, how can we apply this to our classroom? Now, for this one here, it's very hard to see the magnetism in space. However, you can use here our phones. Let's see. So you can use a student's phone to be able to see the magnetic north at the school you're at. You can also look at some maps to see that if you take a map of, let's say, Toronto here in Canada, compared to a place in Europe, in Africa, in Asia, or even in South America, the way the magnetic lines will be changing, because the magnetic north is changing every year, and also depending where you are on the planet, the direction towards the north magnetic pole or the south magnetic pole would change. So I think that could be something that students can do. And if you have magnets and you have also iron filing, you could see how the iron filing is affected by a magnet, but also what happens to the metal filing when you have a second magnet getting close to the first magnet, and see how their magnetic field lines are affected. So I think these are good possibilities with respect to magnetism and putting it with astronomy. So let's see what's the next one. We have the next generation lunar reflector. Okay, so that is quite exciting as well. So it looks like this. So this one here is blocked. I was able to see a better picture. Let's see if I can see the better picture. The better picture is right here. So not this one. Okay, it is this one right here. Perfect. So it looks like this. So it is 3 mirrors at 90 degrees. So what happens is, regardless of the direction, we have a laser coming here. It is reflected 2 or 3 times, and it's going back exactly in the same direction that the laser is from. So what happens here? So we have here lights to be able to see, first of all, the distance between Earth and the moon. Second, we are learning more and more on how to communicate with laser instead of communicating with radio waves. I know that SpaceX is working with the Starting project using lasers for communication, and also more and more NASA and some space agencies are using light to communicate with probes that are going to different planets. Because if you think of Mars, for example, if it takes, I don't know, 8, 10, or 20 minutes for a radio wave to go to Mars and another 10 or 20 minutes to come back, the issue here is that you have a time lapse of could be 20, could be 30, 40 minutes before there's an answer. However, if you're using lasers, it will be a fraction of that time. So that is quite amazing. And so that's something that we could do. I'm sure that we can use, for example, for the classroom, on phones, you can use what we call lux meters to see how the distance between a receptor and an emitter of light can change. So if, let's say, I have my lux meter from 1 meter from a light source, or 2 meters, 4 meters, or 10 meters, we'll be able to change how much light comes to the phone. So that's one thing that can happen. If you're doing optics in your grade, you can certainly use a laser and try to see. It will be hard to find the speed of light with the resources in the classroom, but maybe you could use at angles and try to see if you can have a laser being able to be reflected so that the laser can be aimed at a specific place so that we can use angle to look at this direction of light. So that is a possibility. Why not? The other option we could do as well is the following. Give me a second. I know that if you're using Arduinos, or if you're looking at microbits, they can communicate with each other when they have Bluetooth capabilities, and therefore you can, let's say, if you have, for example, the school, and you cannot communicate from one side to another side, you can certainly have an emitter going from one and then create an array of Bluetooth power of what do they call microbits, or what's the other one? Um, Arduinos, to see if you can do an array to bypass maybe a large object like a building. And that would be useful because when humans are going on the far side of the moon, the biggest issue that we have at this point is how can we have continuous communication capabilities. I know that China has sent, I think it has an orbiting probe right now that allows for such communication on the far side, but it's still limited because the only one I know is from China. So that's something to look into. Let's look at the next one. We have here camera capture interaction between blue ghost moon surface. So this one here, we have, so what's interesting, we have at the bottom of the probe here, or the lander, a series of cameras all around them. And the purpose for that is that when the lander gets close to the ground, it can map the soil. But when it gets closer and closer to the ground, what happens? You have air and gas pushing away dust and regolith and all kind of particles and rocks, even because of the rockets slowing down to the landing site. And as soon as the landing is done, then the engine is cut off. However, with the camera, they can actually map the surface after the landing to see how much dust, what is the volume of materials that have been pushed away. So that's useful for this lander, but will also be useful for any other landers we have. And if you think of the Artemis mission, when we're going to have a base on the moon with several landers coming, we cannot have all the landers coming within 100-meter square. There'll be so much dust and contamination that could be an issue, but that's something that can certainly work. So how can we do this one here with respect to the classroom? We can have, for example, several cameras and try to see if we can do a 3D mapping of an area. We can do 3D mapping, for example, or if we can't, at least take pictures where we have, let's say, a vacuum cleaner with air coming out, and then you get it closer to the ground, pushing away the dust, and then you can take a picture before and after to see how much sediments and how much materials have been moved. I think that's something that is a fair experiment. And if you think on the planet here, we have sandstorm. And when you have sandstorm, you have such a lot of big volume of sand moving. They happen on Earth, they happen on Mars. It's also something to study. And I think it's interesting. Okay, so we have here the NASA lander to test vacuum cleaner on the moon for sample collection. Okay, so what does that mean? So here at the bottom of the lander, we have here an arm, and what it is, it has its own set of gas pipe, and you could see here the surface. And the whole idea here is that if you think of, let's take this. Let's say you have this. On my hand is the ground. You have a cup like this, and you can come here. You could decide to have a shovel to take some sediments for study. But imagine if you had a vacuum cleaner, and they call it here a planet vac. When you have gas going in at the bottom here, and another one here like a vacuum cleaner pulling the gas, what happens here is that whatever dust that is here, sediments, regolith compounds right here will be taken out, and then you can actually get a sample of like a lunar sample. There'll be probably samples like smaller than 1 centimeter in diameter, but still, I think it's something that could be interesting. So instead of having people with all like having a backhoe type shovel, like something to get the soil and then put it in a container. There's so many moving parts, it's tricky. Now, they used this type of technology when they went on Bennu to get the asteroid sample, when they used nitrogen. So they just brought a plate, there was a nitrogen gas, and then they pulled in the sample of this asteroid. So it allows here to have very few moving parts and something that is easily available. Now, this can be, I'm sure, created something in a classroom. Most of the, how could I say that? Most of the vacuum cleaner, similar to the Dyson one, when there's no filter, but they're using cones and air only to pull the dirt, would do something similar to that. So imagine if students were able to go on like in the yard and see if they can sample a few areas where they could analyze the type of sediments they can pull. I think that'd be interesting. It could be sand from the sandbox, on the schoolyard, on the pavement, in the grass. What could they come up with? They might even get some insect. What happens if they are pulling maybe sediments from the side of a creek or under a forest, like under soil under a forest? A variety of sampling could be possible. So you need a battery powered vacuum cleaner, but I think that's a good one. And I think I'm going to do that one with my class. I think I like the topic. The next one here is regolith adherence characterization. So this one here, it's amazing. So we have a wheel. Actually, it's two wheels, two identical wheels with exactly the same type of materials. Some of those are glass-based, plastic, metals, materials here. And the idea here is that as the lander landed, it put away, it just moved up a lot of dust. And the idea here was to see how much of that dust actually went and got stuck on these materials. So that was the first one. So one is open to the environment, whereas the identical wheel on the other side actually is hidden from the environment. So you end up with a pristine materials. Let's see if I can show you the two side by side. And look at this, it's right here. So see, we have one here that is open to the environment. So as the lander came in, let's see if I can make it bigger for you. We have here the lander that landed. We have dust that came up. And here they want to know what kind of materials, the quantity of dust that actually went over and got stuck on the system right here. It's very important because dust gets everywhere. Now, what if you can see, we have here a reader, and here on the hidden part, you have the same wheel with the same materials. So the idea here is that as you are having two cameras or two type of, let's say, experimental reader, or they just scan what they have, they'd be able to compare sample that was in contact with the environment compared to the same materials that was in a sealed environment. And that'll be interesting because that will allow them to be able to compare both materials. That's a great experiment because they didn't have to do the experiment on the moon and find a way to bring it back to Earth for analysis. Analysis could be done right away on the planet. And here, one way you could do this is, for example, you may have, so if you go for a hike in, or you go for a walk in on trails, for example, you know as well as me that if you put dark pants and it's a dusty trail, you end up with the bottom of your pants all brown and with all kind of particles from dust from the time that you walk or because of people that were walking beside you. You also, if you go into and walk in the grass, sometimes you have a little seeds on your pants, and it's something you could look into. So the type of experiments that could be done with your students would be, for example, to have, let's say, sweatpants, and or even sweatpants and pants a bit longer that almost touch the ground, and go for a little walk on the path leading to school, on paths in the school, maybe in hallways at the end of the day in the school where we have dust everywhere in the school. It could also be walking in the field. when you have pollen or insects or twigs that would glue on the pants, and then compare the difference of the type of sediments or organic matter that you can pick up when you walk around. I think that could be interesting related to astronomy. Now, many of the examples I gave today for experimentation in your class also included topics such as ecology, topics such as chemistry, physics as well, with voltage and electricity. So all kind of field that you can bring in your classroom. Now, my ideas are not complete. A lot of these ideas need a little work or need some research. And depending on the age of your students, you might find a way to either have the resource at home from the students, or maybe have a school to be able to buy some of these materials, or be resourceful with the equipment you have. On this, hopefully you have enjoyed this video. And I'm going back here to this sunset on the moon. So we've talked today about the Firefly Blue Ghost Mission 1. We've talked about the fact that they are actively looking for new experiments to put on their mission 2. I also look at all of the experiments and how those experiments could have something that could be done in the classroom, as if we were going to another planet similar to our Earth and wanted to do some sampling. Anyway, these are ideas. I always like to do hands-on activities in my class. And one of the reasons I did this video was to be able to research and think about it so I can bring that in my classroom, because I'm going to do the astronomy unit in about a month. On this, have an excellent day. If you have any comments and insight on these topics, please put them in the comments below. I'm always curious in reading your comments. On this, I'm going to put here a link to on this side or this side. On this, take care. Bye-bye.